So this is chapter 7. So we're going to be talking about linear regression or regression kind of in general, but particularly linear regression. So this is piggybacking on what we discussed in chapter 6 with the scatterplots. So a lot of the things that we talked about, we're going to bring into this chapter. And then we're going to talk about kind of what we can do with that information that we can get from a scatter plot. So we have an example here. If you look at different Burger King items, every item you can get the protein amount and you can get the fat content, and maybe there's some relationship with that. So we have a whole bunch of data points here, and you can see if we think about what we talked about in the last chapter, how there is a positive relationship. If we talk about the strength, we might say that it's moderately strong, maybe getting close to strong relationship. Definitely linear. So you definitely have a linear trend here. And so maybe we could find some way to make predictions. If we know one of these variables, we can make a prediction on the other one. And so that's what this chapter is doing. We can see we're given the correlation is 0.76. If you remember from chapter 6, when we did correlation coefficients, the closer the correlation is to 1, the stronger the fit is, the stronger the relationship. And so this is getting kind of borderline moderate to strong relationship. And so we can talk about what is the line. So obviously you could draw many lines through these points. I mean, there is a line that goes through the points, or there is a line that goes through the points. But what is the best line? Obviously, these are not very good. Obviously, probably the one that's already on there is the best one. But how would we find that? And what does that mean exactly? So first, let's talk about how we can find that and what makes it a good line versus a not so good line or even a bad line. Well, we're going to talk about this concept of a residual. And so what the residual is, any of these data points here, any of the actual data points, we could label with an ordered pair XY. And then we're going to, what we want to do is we want to use the X data point. So if this item has 31 grams of protein, what would we predict would be the fat content in that item? And that's kind of the idea. So we're going to use the X value to predict what the Y value would be, or we're going to use the protein in this case to predict what the fat is going to be. And if we have this line that's coming through these points, and we can take, so they're using this point down here, what is the vertical distance to the line? And the difference in that, the X value is the same. So you can see that we have the ordered pair XY for the actual data point. And then if we go straight up to wherever this line is, the X will be the same because we're not moving left to right. We're just moving straight up. And then the Y is going to change. And this Y value for that point there would be a predicted value. And so we call this Y hat with a little triangle over the top of it. We call that Y hat, and that is the predicted value. And then the residual is just the difference. So the residual is, we could say observed value minus predicted value. And what the line of best fit does is it tries to minimize overall the residual. So we could find a residual for any of these points. And you can see some of them were really close to the line. Some of them, like this one, like these down here, they're getting farther from the line. But you can also see we have a good mixture of some that are above the line, some that are below the line, and so on. So residual observed minus predicted. Like I just said, points above the line will have positive residuals. So all these have a positive residual because the actual data point is higher than what you would predict. So the prediction is on this red line. Points below the line have a negative residual. This line gives average fat content expected for a given amount of protein. So for instance, if we have an item with 15 grams protein, we would predict we would have about 21 grams of fat for that item. If we have 30 grams of protein, we would predict we have 35, 36, whatever that would be coming up here. And we can see that several points would be above the line when we're at 30, several points would be below the line. And it's kind of that way all the way till we get up here where we get more rare items, and these happen to all kind of be above. But overall, we get a lot of below, a lot above, and it averages out. So the best fitting line will have the smallest residuals. So like I showed you in the first slide, if we did a line like that, if it's a straight line, these would have really high negative residuals. These would have really high positive residuals. We don't really have any that are close. The best fitting line has small residuals. So we obviously want the line to be closest to all the points. High negative residuals are just as bad as high positive. Particularly just generally speaking, when we're talking about finding the line of best fit. Negatives are just as bad as positives, and we just want them to be close. If we square the residuals, that makes them positive. The line of best fit is the line for which the sum of the squares is the smallest. So we're going to get each of these residuals. So this would be a negative residual. You square it, it makes it positive. Positive residuals, of course, you square, make it positive. And we can add all those up, and we want that sum to be the smallest, as small as it could possibly be. All right, so from algebra, when we talk about linear equations, linear functions, they have this form, y equals mx plus b. M, of course, is the slope, which everyone probably knows, and then the b is the y-intercept. And so at the line of best fit, it's an equation of a line, so it's going to look like y equals mx plus b. We do this a little bit differently here, though. So we use y hat because we're trying to make a prediction on y. And then we do a b subscript 0 plus b subscript 1 times x. And the reason, so it is flipped. We have the x in the second term on the regression equation. We have x on the first term, typically with the algebra equation. But obviously addition is commutative, so you can switch them around. But the reason we kind of do this in this order is because you could, and there is a chapter in this book that we're not going to cover, but you could talk about multiple regression. So you could have other X values that you're trying to use to make a prediction on fat in this case. So maybe you have protein, maybe you have sodium, maybe you have I don't know, sugar content, something like that. You could have other variables that you're going to use to make a prediction on fat. And so if you were doing multiple regression, you'd have B1, X1, and then B2, X2, and then so that way doing it this way, you can just kind of add these at the end. But we're not worried about that. We're only doing this singular linear regression. So B1 is the slope. Now, what does slope mean? So that's very important. A lot of times we don't talk about this in algebra classes. Sometimes we do. Some algebra classes will get to it, but not always. When we talk about slope, we mean, so everyone knows slope is rise over run. The rise is the change in the y. The run is the change in the x. So basically what the slope is telling you, well, for instance, if the slope is 5, what does that mean? That means that you go up 5 over 1, up 5 over 1, up 5 over 1. So the rise is 5, the run is 1. Its slope is -5, you go down 5 over 1. So this is how we interpret slope. As x increases by 1, y increases or decreases, depending on if it's positive or negative, by b1. And that's kind of a general case of, or a general explanation of what the slope means. And since we're talking about regression, we probably need to call that y hat. And probably if you were to write this out, you should probably say y hat is y is predicted to be whatever the slope is. And we'll do some examples and we'll write this out. B0 is the y-intercept. What does that mean? Well, the y-intercept is wherever it crosses the x-axis. And what's the x value at the y-axis? What's the x value at the y-axis? The x value is 0, and then the y-intercept is whatever that y value is. So when, if we're interpreting the y-intercept, when x equals 0, let's try this again. When x equals 0, y is the y-intercept, be 0. All right, so let's see, let's just kind of speak in general. Let's see how this looks when we use an actual example. So we'll talk about how to get this equation, but here's the regression equation for that Burger King data. So the slope is 0.91. And so what that means is a Burger King item with an additional gram of protein, so that is X, is expected, that's the predicted part, to have B1 additional grams of fat. All right, so you can kind of see how as X increases by 1, so Burger King item with an additional gram of X, gram is units, of course. So when X increases by 1, Y hat or Y is predicted to be B1. All right. And you can pretty much, these pretty much follow the same format for writing this. Obviously, you could probably phrase it in a different way, say the same thing, but basically we're gonna say it they'll be said this way. Then we have the y-intercept is 8.4 when X is 0. So that means a Burger King item with no protein. That would mean X is 0. It's predicted to have Y be the y-intercept. So it's predicted to have 8.4 grams of fat. And this one, definitely you could, there are ways to say this that sound better than others. So if you say this literally, I guess for this problem, you might say when protein is 0, fat is predicted to be 8.4 grams. But that's correct. That's fundamentally correct, but it sounds better to kind of say this in a more natural way. So in other words, if you ever have to write this out, say it in a natural way. Try to say it correctly, but say it in the most natural way possible. All right, so let's look at another example. So we have a linear model for hurricanes. So this takes the central pressure. So looking at the central pressure of a hurricane, and then predicting what the maximum wind speed is. And so we can see pretty strong correlation. Correlation is negative 0.898. So that's actually very strong. Closer you get to -1, stronger the correlation is. Negative, like we said, and then linear, of course, which is what we're also looking at. So the slope is negative 0.9748. And so what that means, now, whenever I teach this in a live class, I always ask, does anyone know what MB stands for? And I think I may have had one person over the years say that they did. And the point is, it's not important, and at least for what we're doing. We're just trying to understand what the slope is telling us. We're trying to understand what the y-intercept is telling us. So it doesn't really matter even if you don't know what central pressure is exactly talking about, even if you don't know what MB stands for, you can still interpret this because we're just kind of following a format to interpret the slope. Slope is the important thing, not necessarily what the particulars of the data and what the data is measuring. So in this case, for every 1 millibar, that's what MB stands for, increase in central pressure. So when X goes up by 1, we can expect, or we will predict, or Y is predicted to decrease because it's negative 0.9748 knots at the maximum wind speed. So you can see this is again saying the same thing. So one unit of X, and that's standard, just 1 unit increase corresponds to the slope increase or decrease. So there is our slope, the decrease because it's negative, and then that is our Y. So follows the same format again. And then if we talk about the y-intercept is not meaningful since 0 millibars of central pressure cannot happen. Now, maybe you don't know that. I may not know that other than doing this example. So how would you know that? You could figure this out by looking at the data, and we'll talk about this some in the next chapter. But if you look at where are all the X data points? They're between 920 and 1,000. This one a little bit above 1,000, nothing really below 920. So this is what's called extrapolation. And extrapolation is when you have your range of data, 920 to 1,000. You don't really want to make predictions outside of that range, at least not very far out of that range. You might be able to go a little bit out of the range, but you don't want to go far, and especially not all the way from 920 to 0. So that would not work at all. And 1,000 knots, if you don't know how much that is in miles per hour, it's a lot. So not going to happen, but you can mostly tell that by where is our range of data. You're not going to go all the way down to 0. If we look at the Burger King example and where that data was, we have 60, we go all the way down, it's going to go down to 0. And also, well, we'll leave the intuition out. But this does go down to 0. So it is reasonable to make a prediction on X being 0. So again, even if you don't know what X is referring to, or you don't know much about X in this case, you can still make an intelligent observation like that. All right. Use the line of best fit. So for the Burger King example, again, to make a prediction for the fat content of a tender crisp chicken sandwich, which contains 31 grams of protein. So all we're going to do here is we're going to plug in the 31 into the equation. So 8.4 plus 0.91 times 31, and plug that in the calculator, and we get 36.7 grams. One thing to mention, just kind of as an aside, because you may see this at some point. In this case, protein has units of grams, and fat also has units of grams. They don't have to have the same units to do this regression. Obviously, central pressure and speed do not have the same units. But for instance, if you were looking at sodium and making a prediction on fat, sodium would probably be measured in milligrams. Fat would still be measured in grams. If you said what would you predict the fat content to be for an item with this many milligrams of sodium, you would still just plug it in, and you do not have to change units to convert it to grams in fat, because it's automatically going to do that. Whatever the units are here is fine. Whatever the units are here will be fine. You never have to convert units, in other words, so don't worry about that. And it's obvious when you have one like this where they're completely different. You can't convert millibars to knots anyway. But it can be a little bit confusing if you see milligrams here and grams here, but you do not have to convert. Never convert, just plug it in and you get what you get. All right, so find the residuals. So we need the actual data point. So the actual for this is 22 grams. So the residual is observed minus predicted, or actual minus predicted, and we get negative 14.7. And here, so in specific cases, we said at the beginning that negative residuals are just as bad as positive residuals. That's generally talking about where the line should go. So you want it in the middle, not completely below or completely above. But if you're talking about actual data and actual conversation, it could be bad or good, like personally, I guess. For instance, would you rather over predict the fat or under predict the fat? You'd probably rather under predict. So you'd probably rather get less fat in this case, but maybe in other cases you might want to get more of whatever it is. So generally speaking, positive residuals negative residuals are equally bad or good. But in specific cases, you might be able to say you'd rather have one than the other. So that's the point there. All right, so we'll stop this and pick it up in the next section.